Hello and welcome to today's video of the video series from reinforcement learning. Today we are going to talk about Q-learning and we're going to see it with an example from the Tower of Hanoi. As you might remember from last time, reinforcement learning is one of the three major topics from machine learning, and now Q-learning is going to be one algorithm in reinforcement learning. Before we start with reinforcement learning, I just quickly want to talk about the Tower of Hanoi as we're going to use it as an example today. The Tower of Hanoi consists of three different stacks and any number of disks. In the beginning, all of the disks are going to be on the same stack. Here it's the middle one. Later on in our example, it's going to be the left pile. It doesn't really matter. The goal of the game is to move all of the disks to a different stack, and there exist some rules. The first one's pretty obvious because it's kind of a physics rule, I would say. We can only move the disk from the top of the pile, and the second rule is that any disks that we are moving, we can only place either on an empty stack or on a stack where the smallest disk, so the disk on the top of the table, is going to be bigger than the disk that we are moving. That might sound a little blurry right now, but I guess it's going to be clearer throughout the video. Getting into Q-learning, again, we have a set of states as in every reinforcement learning problem. Here it's going to be a discrete set of states, and they are represented by a tuple in which the nth index corresponds to the nth position, to the position of the nth biggest disk. Again, this might sound a little blurry, but no worries. It's going to be clearer when we see an example. So here we have the picture again that we have seen before, and we have 1, 2, 3, 4, 5, 6, 7, 8 disks. So it's the eighth tuple, and all of them are on the second stack. So the eighth tuple would be 2, 2, 2, 2, 2, 2, 2, 2. Another example we can see with the initial state and the goal state. Here we only have 3 disks, so it's a little easier. In the initial state, as I said before, here our disk on the left side would be 1, 1, 1, the goal state 3, 3, 3. And the amount of states is to be to the power of n. That makes sense, as for every disk, it can be on all 3 different positions on all different stacks. Yeah. Then also we have a set of actions. There's really not too much to say about it. An action we can just see as moving from one action, from one state to another state. And then we have the reward function, which gives every state and every action in every state a reward. Here we have an example for the 2-disk reward matrix, just 2 disks because it's just a little easier. We see here a lot of rewards from negative infinity that are all the moves that are impossible or that are not allowed. For example, we see that we have here from 0, 0 to 0, 1, negative infinity. The second disk would be the bigger disk, and so it's not on top of the table of the stack, so we can't move it, so it has negative infinity. All the possible moves that we're actually allowed to take, we see a 0, except 2 states. On the right column we have a reward of 100, and that are the 2 possible actions that move into the winning position and therefore are rewarded with plus 100. Then we also have an action value function. We already talked about it in our video about reinforcement learning. Here it's a Q table. So there's a Q value for every action in every state. It's being initialized with all zeros, and this is what we want to learn. We're going to update it, and our goal is to updated as closely as possible to the Bellman's equation. The Bellman's equation, as we see here, is an expected reward, and it's the expected reward that we have for the reward from t+1, so the immediate reward that we get for our action in our state, and then we add the maximum of all future awards if we have the optimal equation, and we're going to multiply this with gamma. We've talked about gamma before as well. It's the discount factor, and that is bigger than 0, smaller than 1, and just makes sure that the future rewards are not taking into account as much as the immediate reward. And then we're iteratively updating that with the learning factor, and that just works the way that our Bellman equation that we calculate, we multiply it with A, our learning factor. Again, this is smaller than 1, bigger than 0. And then the rest of the alpha, so 1 negative alpha, we're going to multiply with our old value. And so as bigger our alpha is, as more we're learning the new value, and as smaller it is, as more we're sticking to the old Q star value, the old Q value that we had. And then last but not least, again, we have a policy. The policy is also pretty easy, because then when we're done with all our training phases, it's just going to be the biggest, the highest Q value for every state is going to be the action that we are going to take. So the action, as I said before, the next state in which we want to move. Having that said, we also tried it with the towers of Hanoi. We used 4 disks, and we can see here that it worked pretty well. On the x-axis, we see the numbers of training episodes, and it needs quite a lot. So we are with somewhere between 10 to the power of 3 to the power of 4, maybe between 6 or 700 twice until it really gets good. And on the y-axis, we see the number of moves that our agent needs in order to solve the game. And then he can actually learn the optimum of 15 moves. So optimum in the Tower of Hanoi is always n 2 to the power of n negative 1. And yeah, so after about 600 or 700 moves, our agent can actually learn the policy in order to solve the Tower of Hanoi optimally. Thank you very much for watching, and see you soon.